Welcome to this explainer. Today we're taking some pretty complex technical reports and transforming them into clear, actionable architectural blueprints. The goal? To completely demystify artificial intelligence. We're breaking down a massive engineering analysis on the logical design of intelligent systems, turning abstract concepts into a structured, governable blueprint that you can actually take and apply to your own work. Let's get right into it. So let's kick things off with a fundamental question that really sets the stage for everything we're about to uncover. Think about the standard apps you use every single day. Most of them do exactly what they were programmed to do, right? Nothing more, nothing less. But AI is fundamentally shifting that whole paradigm. So where exactly is the dividing line between just a standard application and a truly intelligent system? Well, at its core, an intelligent system makes this massive shift from just using static logic to possessing actual statistical intelligence. It's not just running fixed code anymore. It's continuously learning, it's adapting to its environment, and it actually improves over time just by analyzing data and observing how users interact with it. It's software that literally grows.
To get a grip on this, here is the architectural roadmap we're following today. We're going to start with the foundational requirements, map out the logical architecture and decision models, look at how these systems actually learn, tackle the necessary governance and security, and then finally tie it all together with real-world applications.
All right, Section 1. Let's start building our foundation by looking at the fundamental goals and requirements of these systems.
You'll notice a really stark contrast between these two paradigms. Traditional software relies completely on static logic and explicit programming, but intelligent systems, they require continuous adaptation. And because they're constantly ingesting real-time data and making autonomous decisions, they demand incredibly rigorous non-functional requirements. I mean, we're talking about the absolute need for ultra-low latency and extreme robustness. Because think about it, when software thinks for itself, a slight lag in processing isn't just an annoyance, it's a complete system failure.
Moving right along to the logical architecture. Let's go under the hood and look at the actual data pipeline that makes this continuous evolution possible.
The absolute crucial point here is understanding this chronological flow of data. It's an elegant 5-step journey. First up is ingestion, where sensors or APIs are pulling in raw data. Second is pre-processing, so cleaning and validating all that data. Third is storage, often using a massive lakehouse to hold both raw and structured information. Fourth, we hit inference, which is where the machine learning models actually analyze the data to make a decision. And finally, action. This is where the system triggers a tangible, real-world response. When you trace this architecture end-to-end, you can really see how sensors feed directly into those ingestion and transformation layers. That refined data then drops into the data lake, which basically acts as the central brain's memory. That memory powers the AI models and rule engines to drive that final action on the other end. It's just a beautiful, continuous, closed-loop system of intelligence. Okay, part 3. Let's zoom in a bit closer and look at the gears of our machine, the decision models that dictate how the system actually thinks and evaluates information. A great way to understand this is by comparing two totally different approaches to decision-making. On one side, you've got the raw power of deep learning and neural networks. Now, these are incredible at finding super complex patterns in massive data sets, but they act as an uninterpretable black box. You don't always know why they made a certain decision. On the flip side, you have traditional logical rules. This is your classic, highly explainable if-then logic. Clear? Yes. But it's rigid and it can't adapt. Honestly, the real magic happens when engineers build hybrid architectures that combine the pattern recognition of deep learning with the strict safety rails of logical rules.
But the system has a much wider toolkit than just neural networks and basic rules, right? Depending on the problem, it might use probabilistic or Bayesian models, which are absolutely fantastic for handling statistical uncertainty and noise. That makes them perfect for things like medical diagnosis systems. Then there's fuzzy logic, which handles imprecision. So instead of a strict true or false, it understands degrees of truth, like evaluating what exactly constitutes a high temperature. And finally, you have reinforcement learning. This is your go-to for long-term optimization through trial and error, like teaching a system how to navigate a highly complex physical environment.
Moving into Section 4. Once we've got a decision model in place, we really need to understand the mechanisms that allow it to learn and update. Basically, how does the system actually get smarter? Well, there are 4 main updating mechanisms driving this evolution. First is batch learning, which is basically offline training using massive sets of static historical data. Then you've got online, or incremental learning. This is huge because it allows the model to continuously update its parameters in real time as new data flows in. Next is transfer learning, which is a massive time saver.
You basically take a model that's already been trained on a colossal dataset, like a GPD model, and just fine-tune it for your highly specific task. And lastly, reinforcement learning, where the system learns dynamically from its environment using a system of digital rewards and punishments.
Now on to Section 5. With all this autonomous intelligence comes the absolute necessity for a strict safety harness. Obviously, we can't just have systems making decisions out in the wild without serious guardrails in place.
To manage the inherent risks of the real world, we have to implement several layers of governance. We absolutely need explainable AI, or XAI, using tools like Lime or SHAP, just to make sure humans can audit the process and actually trust the AI's decisions. We also have to mathematically manage uncertainty, so the system explicitly knows when it's unsure of a result. Plus, privacy by design is non-negotiable. We should only collect exactly what we need to comply with legal frameworks like the European GDPR and the Brazilian LGPD. And of course, wrapping all of this up, we need incredibly robust security to protect these models from malicious adversarial attacks.
All right, Section 6. Let's take all of these abstract architectural concepts and anchor them into tangible reality. We're going to dive into 3 very distinct case studies that show exactly how this blueprint comes to life.
For our first real-world application, we are looking at one of the most complex engineering challenges of our time, the autonomous car.
Now, an autonomous car relies heavily on edge processing. That means the computation is happening right there inside the vehicle, not miles away on some distant server. It's ingesting massive amounts of data from LiDAR and 360-degree cameras, using deep neural networks like CNNs to literally see the road, and SLAM mapping to understand exactly where it is in that environment. At the same time, it has hard traffic rules embedded for safety. And the performance requirements here? Staggering. It demands under 100 milliseconds of latency. Think about that. It even uses fuzzy logic to safely navigate the unpredictability of heavy rain or snow, all while receiving continuous over-the-air updates, so the driving model just keeps getting better.
Let's completely shift gears and look at a totally different environment. We're moving from a single vehicle to an entire city grid with smart urban traffic optimization. So instead of steering a car, the goal here is to optimize flow and crush citywide congestion. You have edge controllers sitting right at the intersections, gathering data and firing it off to a central server. That server uses reinforcement learning to dynamically adjust the traffic light timing based on real-time traffic flow. And there's a really brilliant architectural choice here. Because this system relies on anonymized public transit and vehicle count data, it carries a very low GDPR privacy impact while delivering massive public value. It's a win-win. For our third and final case, let's step off the streets and inside a factory to take a look at smart textile manufacturing.
This system is honestly a masterclass in hybrid decision modeling. It's processing high-resolution imagery from the production line, right there on the edge. It uses convolutional neural networks to spot incredibly subtle visual defects in the fabric. Then, it seamlessly applies fuzzy logic to smoothly determine just how severe that defect actually is. And finally, it relies on a rigid traditional rule engine to instantly halt those massive production machines if a critical issue is detected. It is the absolute perfect blend of modern AI vision and traditional industrial safety logic.
Bringing this all together, the source material really hammers home a core philosophy that every engineer needs to remember. True success here lies in balancing traditional software robustness with continuously evolving intelligence. It's simply not enough to just build a clever AI model anymore. You have to build a complete system around it that is reliable, secure, and maintainable over the long haul.
So, we've demystified the gears, the data pipelines, and the strict governance that make these systems tick. Now, the ultimate question is over to you. We are officially past the era of AI being just a magic black box, and we're entering an era of structured, governable engineering. Armed with this architectural blueprint, what intelligent system are you going to build next?